Okay, let's see. You want to put your headsets on? You want to put your headsets on? Does everybody know how to work your headsets? Yeah, okay. Yeah. All right. Well, thanks so very much for staying till the very end. And indeed, you'll enjoy it because Dr. Patrick Taylor, who is an Arctic scientist at Langley Research Center in Hampton, Virginia, is an absolute expert studying the climate of the Arctic area and see how it changes over time. His research really focuses on the consequences of the rapid changing Arctic. In fact, most recently, he's been using a variety of NASA science data to better determine the role of clouds in the Arctic climate change activities that he's been doing. So, Patrick, take it away.
I've learned a number of things about myself and about the world on my 15-year journey through science. One of the most important lessons I've learned is that we live on an interconnected planet. This means that our actions affect others, and the actions of others affect us. This may sound obvious, but my epiphany really was that our climate system makes this effect operate at a global scale, and that our actions affect the lives of people that we will never meet. My name is Patrick Taylor, and I'm a climate scientist at NASA Langley Research Center. Over the next few minutes, I'd like to share with you a bit about how our climate system interconnects us and what NASA data is telling us about the rapid changes in the Arctic. Next slide. If I could only choose one animation to demonstrate the interconnections of our climate system, this would be the one. This animation shows data from NASA's GEOS modeling system. What you can see here are the many parts of Earth's atmosphere evolving together and connecting our planet. Whether it be the Saharan dust particles in the tan colors being lofted and carried across the Atlantic Ocean by the winds that are then further dispersed globally, or the mid-latitude storm systems marked by these swirling cloud fields that are carrying air from China to the US, and then air from US and Europe into the Arctic. Our planet is interconnected, and at NASA we collect data every day that illustrates this. Next slide. The largest source of NASA data comes from satellites. Here is a picture of NASA's Earth observing fleet. These satellites measure temperature, clouds, dust, sea level, sea ice, and ice sheets, just to name a few. NASA currently operates more than 20 satellites, focusing on a lot of different science, all aimed at understanding our planet for the benefit of humankind. One question you may have is, why are there so many satellites? I like to think about Earth's climate like a puzzle, with many pieces. The pieces of the atmosphere, ocean, plants, animals, ice, and of course humans. No one satellite mission is able to address all of these interconnected pieces, so we need many satellites to get a full picture. From space, we've seen a lot of changes over the last 40 years. The story of the Arctic represents one of the most rapidly changing regions on Earth. These changes not only affect the people living in the Arctic, but have consequential impacts on natural and human systems throughout the world. What happens in the Arctic doesn't stay in the Arctic. Like throwing a rock in a pond, Arctic climate change has ripple effects with a global reach that affect our food, energy, health, and water systems, as well as global security. The Arctic is also a prime example of the interconnectedness of our planet, with broad implications for climate change. Next slide. Global temperature is one of the most widely used indicators for climate change. Based on the NASA record of global mean surface temperature, the globe has warmed by about 1 degree Celsius since 1880. That's shown in this animation by the increasingly red color of the planet as we move forward in time. More striking than this is that the 21 warmest years on record have all happened in the last 23 years, since 1998. So what this means is that a 23-year-old person and a 100-year-old person have both lived through the 21 warmest years on record. That's astounding. The increase in global temperature is due to the increase in atmospheric carbon dioxide or carbon pollution as a result of human activities and burning of fossil fuels. A key aspect that is evident is that not everywhere on the globe is warming equally. You can see that by the red and blue splotches that are popping up across the globe. The Arctic, however, is found at the top of the planet and is underneath what I like to call a red cap. What this shows is that the Arctic has warmed about 3 times faster than the rest of the planet. And with all that ice in the Arctic, a small change in temperature can make a big difference. So a big change in temperature can make dramatic differences. Next slide. One of the most iconic images of Arctic climate change is the rapid sea ice decline. Routine monitoring of Arctic sea ice from space began in 1979. The white areas in this map show the September sea ice extent in each year. The red line in front shows the integrated area. The reason we consider September is that it marks the annual low point of Arctic sea ice extent and shows the most rapid changes. The data show that the last 14 years are the 14 lowest years of Arctic sea ice extent on record. Overall, September sea ice has declined by about 13% per decade, which is roughly 3 million square kilometers. To put that into perspective, and sorry for the US-centric example, but this is roughly equivalent to the area of Alaska, Texas, California, and Montana combined. Now, I hadn't realized this. I hadn't appreciated the full size of Alaska, but Alaska is 3 times the size of Texas. So really, this is 4.5 times the land area of Texas that we've lost in Arctic sea ice extent. One of our goals at NASA is to provide data to provide a better understanding of the factors that are contributing to the sea ice decline, because this will allow us to make better predictions and to plan for the future and protect people. Next slide. Sea ice extent is only one of the important characteristics of sea ice that influences the Arctic climate system. And from a climate perspective, the volume of sea ice is just as important. One way you can measure the volume of sea ice is to track the age of the sea ice. So every year, the sea ice melts during the summer and freezes during the winter. Sea ice that survives this summer melt season is said to have aged. This animation shows Arctic sea ice extent and age in each month from 1984 through present. The gray contours show you the younger sea ice, and the whitest and brightest contours the oldest sea ice, which can be older than 4 years. In 1984, Arctic sea ice was dominated by this older multi-year sea ice. However, since there's been a rapid decline in this sea ice, where the oldest sea ice, older than 4 years, in 1984 accounted for about 20% of the total ice cover. Now it only accounts for 3%. This change is important because multi-year sea ice is much thicker and can grow up to about 4 meters thick. I know it's hard to tell on the screen, but I'm a tall person, about 2 meters tall. So take a look around the room and find the tallest person you can see. That person is probably close to 2 meters. Picture yourself standing on that person's head. So that is about 4 meters tall, or the thickness of multi-year sea ice. By contrast, first-year sea ice that grows only during a single winter is at most 2. So just about to the top of that person's head. It takes much less energy to melt thinner sea ice. So the Arctic is expected to become much more variable, in particular sea ice cover, as approximately 70% of the Arctic sea ice is now seasonal. One of the key questions scientists are asking is how will these energy flows be changed as a result of the changes in sea ice? Well, what we've learned is that warming the Arctic is not only affecting sea ice, but the warming is in part driven by sea ice loss. This means that Arctic sea ice itself is partially responsible for the extra warming that we're seeing in the Arctic. And NASA has some very recent data that illustrates this. Next slide. So NASA data illustrates firsthand what scientists refer to as the surface albedo feedback. That is, the same places where we're losing sea ice most rapidly, those places are also experiencing the largest increases in absorbed sunlight. It works like this. So sea ice is bright white, meaning that it reflects a large portion of incoming sunlight back to space. When covered by fresh snow, this can be as much as 90%. As the Arctic warms, the melting sea ice is uncovering a darker ocean. This darker ocean absorbs about 94% of the sunlight. This warms the surface and promotes further sea ice loss, an amplifying feedback loop. So this animation from NASA satellite data illustrates observational evidence for this process, and it provides direct determination for the size of this process and a key piece of information to help improve predictions of the Arctic. Next slide. It's not only sea ice, but land ice is also being affected by the warmer Arctic temperatures. The Greenland Ice Sheet, in particular, is melting rapidly. NASA's GRACE data has shown that Greenland has lost a significant amount of ice around its edges while accumulating a little bit of extra snow in its interior. Since May 2002, the Greenland Ice Sheet has lost an average of 279 gigatons per year of mass. To put that into perspective, this is the amount of water that can fill more than 140 million Olympic-sized swimming pools each year. This is roughly an Olympic-sized swimming pool the area of Greece. First, instead of filling up Olympic-sized swimming pools, the ice loss from Greenland is filling the ocean. Since 2002, Greenland ice sheet melt has accounted for about 25% of global sea level rise. Next slide. Global sea level is an important climate change indicator that demonstrates the global implications of Arctic climate change. Now, NASA, in partnership with the French space agency CNES, has been tracking global sea level from space since 1992. This visualization shows total sea level changes between 1992 and 2019. The blue regions represent areas where sea level has gone down, and the red regions where sea level has gone up. Global mean sea level has increased by 0.2 meters since 1901. However, sea level rise has accelerated in recent decades. The rate of sea level rise has nearly doubled in the most recent decade from the rate that was observed between 1971 and 2006. Said differently, about 1/3 of the total sea level rise that has occurred in just the last 25 years. Next slide. This brings me to my final animation on the Thermohaline Circulation, or the global ocean circulation. So think of the Thermohaline Circulation like blood moving through your veins and arteries. It's Earth's circulatory system. The heart in our body is responsible for pumping blood. In the case of the Thermohaline Circulation, it's gradients in temperature and salinity that provides this pumping mechanism. Your circulatory system moves blood around, connecting all parts of your body. The Thermohaline Circulation does something similar for our climate, transporting water and energy from the tropics to the poles and back again. A particularly important part of the Thermohaline Circulation here in the North Atlantic is called the Atlantic Meridiano Overturning Circulation, or the AMOC. The rate of deep water formation in this region helps set the speed of the global ocean circulation. And what research has shown is that the Greenland mass loss is freshening the North Atlantic water. This is impacting not just the circulation of currents in the North Atlantic, but the global ocean circulation as well. Again, showing the interconnectedness of our planet. In closing, please take this away with you. We live on an interconnected planet. So what happens in the Arctic doesn't stay in the Arctic. The consequences of Arctic climate change to the flows of energy, to sea level rise, to carbon cycle, and to the Thermohaline Circulation ensure that this statement is true. Human activities are putting carbon pollution into the atmosphere, and this is causing warming and contributing to the melting of the Arctic. These Arctic changes are protecting people and animals that live there. But in addition, the melting Arctic is affecting the entire globe by influencing weather patterns, our food, energy, health, and water systems, affecting our security. The best piece of advice that I can give is to always consider and follow the golden rule. That is, do unto others as you would have them do unto you. The interconnectedness of our planet means that our actions affect more than the people in our direct line of sight, but affects people that we will never meet. I think that if everyone internalized this concept and implemented it into our daily lives, we could make this world a better place, one small decision at a time. Every day, NASA data illustrates just how interconnected our planet is. These data are vital to helping scientists solve the most pressing science questions and to help society thrive on this interconnected, rapidly changing planet. Thank you.
right. Really nice talk. You may have any questions? We'll do the golden rule, right? Yes, go ahead. Oh, you'll have to. Yeah, here we go.
Yeah, I guess the question would be to what extent the simple rule of has this affected sea level rise? Because that was not raised. I mean, it was discussed about the change in the circulation, and Greenland was particularly impressive. But what about the sea level rise from the, which is it too simple a connection, I guess?
Yeah, it's a good question. It's a complicated one. In general, there is sea level rise, but there's also water redistribution. So we find that sometimes there's more rain in certain areas that haven't had it in quite a while. But indeed, the trend is that the sea level is going up, and it'll only continue to do that. Gavin. Yeah, please give Gavin the mic.
Is this working? Yes, now it's working. Yes, yeah. So let me allow me to kind of expand on that a tad. So obviously the loss of mass on Greenland is contributing to sea level, combined with the Arctic loss. So there's not quite as much, but a similar amount of loss from West Antarctica and the Antarctic Peninsula. That's adding. I think it's like 1.2 millimeters a year of global sea level rise. One of the interesting things that happens, though, is that it distributes it in weird ways because there's this gravity effect. So as Greenland loses mass, there's less gravity towards Greenland, and so actually right next to Greenland, if you melt the ice, the sea level goes down, and then in the rest of the world it goes up more. And so you get these kind of odd teleconnections from where the mass is being lost to what the sea level is. That is not straightforward. And then you have the changes to the circulation, which also affects regional sea level. And so you look at places like the U.S. East Coast, and that turns out to be a hotspot for sea level. It's rising significantly faster than the global mean as a combination of changes in the ocean circulation, these patterns of sea level change because these gravity effects, and also it changes the rotation of the Earth a little bit. You have to take that into account. It's a very complicated, like a fascinating scientific story, but also a kind of terrifying story for the rest of the world.
Amazing that is indeed the global observations that are being taken allows us to make those kind of detailed observations and see the interaction between ice, water, land, oceans, and atmosphere. Yeah.
Hello, am I audible? Okay, cool. So I was curious to know, this is, my friend and I were discussing that this is a scary video at some level when you see the red hotspots appearing and so on. But I also think that this could be a great tool for advocacy and for communication. So how does NASA? I mean, I don't know if this is something that falls under your purview, but in general, how does NASA plan to use all this information? Because, of course, this is very useful for research. It's useful for planning. It's useful for all kinds of, policy-making decisions. But to influence public opinion, so because these are brilliant graphics. But how does NASA plan to use this for outreach? Because, as we have seen, public opinion matters a lot for policy-making for any large change. So how do you plan to go about it?
Indeed has, through its Office of Communication, a major infrastructure that uses a variety of social media to be able to get really important scientific discoveries out into the public. Now, that whole environment, we have a lot to learn on how to do that, and it's constantly changing. Different venues, are cropping up that we have to be able to notice and then participate in. Since the pandemic, for instance, a particular type of social media called Clubhouse, where there's a whole variety of rooms where things get talked about and topics enable us to be able to be there and talk about these in greater detail, not just the high-level, superficial sea level rise. As Gavin said, we're talking about sea level rise in some places of millimeters. That seems almost trivial, but when you think about the global effects, and you saw the overall change in the ocean currents and a number of things that this fresh water that's dumping into the ocean has. It's really phenomenal. It's really phenomenal. So indeed, we have a lot more to do in that area, and we're on it.
A question for following up Dr. Schmidt's comment. If you, but he's not. Yeah, you're listening. If you just look at the data set, the satellite data set that with the Topex Poseidon, the radar altimeter going back to 1993, and then the recent mission, the Michael Fry Lake Sentinel-6. If you just look at that data set, isn't the figure of median sea level rise 3 millimeters per year? Is that correct?
Yeah, so the median sea level rise is about 3 and a little bit millimeters per year, and it's been increasing over the decades that we've been measuring that. So there's a measurable acceleration in the rate of sea level rise. As I said, around 1.2 millimeters is from the ice sheets. You have about another millimeter from mountain glaciers, and then the rest of it is made up of thermal expansion. So that as the ocean heat content is increasing, the water is expanding, and so it's a combination of those effects. And then there's some small effects from groundwater depletion, reservoir building cancels that out a little bit. There's more water in the atmosphere, which cancels it out a little bit. But the main things are melting ice, mountain glaciers, ice sheets, and then warming, and those are the two main factors, and that's obviously projected to increase.
Another recent mission called ISAT, and it indeed uses lasers to measure the height of these glaciers and how they change over time. When you look at some of them, you might see the same extent, but in reality, it's being withered down, and we can from that estimate the amount of water that is leaving, and which squirts out the bottom, as you saw in the Greenland animation. So that's an important ancillary set of data that needs to be factored in. So it's a combination of a whole series of measurements that have to be made to look at the estimates and understand where the water is going.
Yeah, I have two more questions. One is about the increase in hurricanes and the fact that they're even thinking of changing the rating, so from 5 to have more, and to what extent that is you can attribute it at NASA at the fact that the sea, the temperature of the sea has increased, so therefore there's more energy, and to what extent is that being used, for example, in the case of the U.S. to predict the hurricane season, and and the fact that you might have to revise upwards the damages that they can cause. And the second question, which is unrelated, is I'm Spanish, so we just had a volcano that is still kind of active. Can you also predict with NASA to what extent this little volcano could actually help a little bit bring the temperature down by cooling?
The aerosols and the atmospheric dust. Let me ask Gavin, who's really the modeler that can answer your first question.
And the second. I'll start with the second. So the La Palma volcano, it's very similar to the Kilauea volcano. It's kind of effusive, but it's not explosive. So in terms of climate, it's only having a very, very local effect on air quality. So it's not going to come up in the in the global temperatures. Like, so for that, you need a very explosive eruption, and it needs to go high. So Pinatubo in 91, kind of reached 15, 17 kilometers well into the stratosphere, dumped many teragrams of sulfur into the stratosphere, and that stayed there for 3+ years, and so that can have a cooling effect. And so, but these kind of small, kind of effusive volcanoes don't really. Now the first question was, yeah. So hurricanes, it's a complex picture. So what we've seen in the Atlantic, we've seen an increase in hurricanes that seems to be tied to the sea surface temperature warming. And we've seen an increase in the strongest hurricanes. So we've seen an increase in intensity, the Cat 3, Cat 4, Cat 5. Now, the hurricanes in the Atlantic don't actually get as big as some of the tropical storms that you see in the Pacific, because they have more time. So some of the super typhoons that we're seeing in the Pacific, I mean, like those are unbelievable storms. And we've been seeing, again, the intensity of those storms has been increasing in line with warming temperatures. However, there are countervailing factors, and so one of the things that kind of mitigates against hurricanes getting stronger is if there's more shear in the atmosphere. So the wind levels, if the wind levels kind of go a little bit more against each other, then that can destroy a hurricane before it forms. And we're seeing some of that, and it's partly because of the pattern of sea surface temperature change. So the whole tropics is not warming altogether, right? So we're seeing warming in the tropical Atlantic, and we're seeing warming in the Western Pacific warm pool, but it's actually cooled a little bit in the kind of the Galapagos region, the Eastern Tropical Pacific, and that pattern changes the atmospheric circulation on the in the equatorial region, and that's changing the shear. And so there's kind of multiple things going on, and so we're seeing trends. But predicting how they're going to go or whether they're going to accelerate is more uncertain than we would like. And so, obviously this is a very hot topic. I mean, we are seeing greater damages, right? But mostly the increase in damages is because we're building more stuff in areas that are prone to being damaged. And so like costs per landfalling hurricane are going up quite dramatically, but partly that's because people are building very, very expensive infrastructure right on the coast where these things are landfalling.
That's great. Okay. Last question.
Okay, hi, thank you. I hope I'm not taking anyone else's slot. So actually this is more from my line of work. So I work in climate risk quantification, climate risk measurement, and we are trying to work with governments and policymakers and some private companies on climate risk insurance. And one question that repeatedly comes up, and I think it's largely because insurance companies don't want to pay up, is when you have, and we work mainly with farmers, so crop risk insurance, but there are other kinds of projects on coastal areas and so on. They always make this claim that, okay, this happened, this natural disaster occurred, but this should be covered by weather insurance and not climate insurance. I mean, it does come back to, exactly, so there's a rain in a desert in India, and apparently that's just weather, that's not climate, according to them. So my organization, I personally, we've been trying to understand how to communicate or rather how to understand ourselves, the line between weather and climate, because I understand that a single event can't necessarily be classified, but how would you say, how would you classify and how would you explain whether an event comprises of weather or climate? And I'm saying that also because, well, clearly the kind of movements happening here are not regular weather events, but how would you communicate that?
So climate really is those long-term trends that are occurring, and fortunately NASA has long-term databases that we've started several decades ago that we've been continually maintaining. And so as we see how they change over time, that really contributes to our understanding of the overall climate of the Earth. And of course, what you're talking about is the local rains, and it's really much more in the area of weather. But if insurance companies are interested in overall climate change to determine then how they would fund or not fund certain areas, maybe that's the heart of what they want to know. There's quite a bit of information around that talks about many of the effects. Now, it's clear there are the gradual temperature increase. We just saw another clear indication of the Arctic sea ice change. Those are major changes due to the long-term climate. Okay, I think with that, thanks so very much for attending. And before everyone leaves, I'd like to thank our staff. You've worked so hard, day after day after day, to make these fabulous things happen, giving us a venue to come up and talk about some of the fantastic research that's being done in many of the agencies in the United States, and of course NASA and NOAA in particular. So thank you very much. I appreciate all your hard work.